In this video, I am going to discuss unit matrix and its construction. In the number system, we have this identity 1 into n equal to n into 1 equal to n, where n is any finite number. In analogy with this, we want to get an identity with matrices. We want matrix A multiplied by matrix B to be equal to BA equal to B, where B is any arbitrary matrix and A is a matrix which plays the role of 1 in this number system. How to do it? Suppose A is a matrix of size m by n and B is a matrix of size n by p, n rows, p columns, m rows, n columns. We have to make these two numbers equal in order that this matrix multiplication is allowed. And carrying out the actual matrix multiplication, we should get a matrix like this of size m by p. The result of matrix multiplication will be a matrix of size m by p. But we want to get b back, ab equal to b. So we want to get the matrix b n by p as the result from this multiplication. So this m and n must be equal. We should have m equal to n, and therefore the matrix A should be of type n by n. It should be a square matrix. And what about B? We have to multiply A with B in the reverse order also. A is of size n by n and B is of size n by p. Then this p and this n must be equal, p equal to n, for this multiplication to be allowed, p equal to n. Therefore, b should also be of the type n by n. So, in order to get this identity, both A and B should be square matrices and they should be of the same size. Let us now explicitly write down the matrix elements of the matrices. Suppose A is a matrix like this. Here A11 means the element of the matrix A at the first row and second column, first row, first column. Similarly, A12 means element at the first row, second column. A13, A1n. This is the first row of A. These are actually symbols. They have their individual numerical values, real or complex. Similarly, the second row of A is A21, A22. A22 means the element at the intersection of the second row and second column. A23 up to A2n, in this way A n1, an2 up to ann. This is matrix A. Similarly, matrix B is B11, B12 up to B1n, and so on. And we want A into B to be equal to B itself. We have written this B here. We want this identity. Now carry out the actual matrix multiplication. First row multiplied by the first column, this multiplied by this should give this result. Similarly, second row multiplied by first column should give this result, and so on. So A11 into B11, we have to write this A11 into B11 plus A11 B11 plus A12 B21, A12 B21 plus A13, B31, and so on up to A1n, Bn1. A13, B31 plus and so on up to A1n, Bn1. This should be the element here. This should be equal to B11. How is this possible? These B terms, they can have arbitrary values, but still this identity can hold only if this A11 is 1 and A12, A13 up to A1n are each 0. If A1, this implies that A11 is equal to 1 and A12, A13, etc. up to A1n are each 0. So the first row of matrix A is like this: 1, then 0, 0, 0, 0. This will be the first row of A. Similarly, if we take the second row and first column, we should arrive at this position: A21 multiplied by B11 plus A22 into B21 up to A2n into Bn1 should give B21. Let us write down. We are taking second row. A21 B11 plus A22 B21 and so on up to A2n Bn1. Second row, first column. Then result will be second row, first column, that is B21. The expected result is B21. This is true only if the coefficient of B21 here is 1, this is 1, and all the other coefficients, A coefficients, are 0 each. That is A21 equal to 0, A22 equal to 1. This is the only non-zero element. Then A23 equal to A24 up to A2n. This is equal to 0. Up to A2n, this is equal to 0. The second row of A becomes 0, 1, 0, 0 up to 0. In this way, we can fill up the entire space and build up the entire matrix A. And then A becomes a matrix like this. We can easily verify. Suppose this is an arbitrary matrix, 2, 3, 4, 5, 6, 7, 8, 9, 10, an arbitrary matrix. And A is written here, of size 3 by 3. We have taken an arbitrary 3 by 3 matrix and taken this is called an unit matrix, and this is unit matrix of size 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. If we actually carry out this matrix multiplication, we will find 1 into 2 plus 0 into 5 plus 0 into 8, that is 2 here. Similarly, 1 into 3 plus 0 into 6 plus 0 into 9 is 3. In this way, if we carry out the actual multiplication, we get this matrix back here. And if we take it in the reverse order, if we take it on the left and the unit matrix on the right, then also actual multiplication will show that this matrix comes here. So AB equal to BA equal to A. Such matrices are called unit matrices. Any matrix element of a unit matrix is written usually by the Kronecker delta symbol, delta ij. Delta ij is 1 for I equal to j, for I equal to j. That is when row index and column index are equal. That is, this delta ii is a diagonal element. And when I is not equal to j, the result is 0 for I not equal to j. Off diagonal elements are 0 and diagonal elements are 1 in unit matrix. This is also called identity matrix because this matrix leaves the other matrix as it is. And we can easily guess that unit matrix plays the role of the identity operator in the theory of point groups. With this, I conclude today. Thank you very much for watching the video.